Whew. Hockey practice was just something else today. I need a cold breather to calm my senses. What? It's not coming out! If only I had a roommate whose name was Patrick Daly and was a chemical engineer.
What? Did someone say Patrick Daly and a chemical engineer? I'm both of those things.
No way! Can you please tell me why it doesn't come out of the kegerator?
Sure thing. We can set up a shell balance on our keg to describe the flow of the fluid through the tube. First of all, we got to describe our system. So here we have the tube with flow through it. This is in the coordinate system of r, theta, and z as a cylindrical system. Let's check out the Kegerator tube. As you can see, fluid flows through the tube in this direction. To describe the fluid through the whole system, we're going to take a small part of the system and describe the flow through that. Here, as you can see in this picture, we've taken a small shell of radius delta r. So from the center to the delta r, to the shell is just r, but from the radius, or from the center all the way to the edge of the shell is r plus delta r. So now we need to set up our momentum balance. The momentum that will factor into this equation is our molecular momentum. So coming in, we have our stress times our area at r. Coming out, we have our stress times our area at r plus delta r. This covers both sides of the shell. As you can see here, our area, because it is a cylinder, can be described as 2 pi r L. Now we need to describe our surface forces. So here we have our pressure times 2 pi r dr, minus our pressure at the bottom times 2 pi r dr, minus our pressure at the top times 2 pi r dr. And we need to describe our body forces of the fluid. So here, F equal, as you can see, as you know from regular physics, F equals mass times acceleration. So in this case, our mass is our density times our volume times our acceleration, which is gravity. So we can further reduce that down to density times 2 pi r dr L, which is our volume term, times gravity. So now if we combine, we can cancel out many different parts of this equation, such as 2 pi over here and 2 pi over there. As well over here we can cancel out r dr, which leaves behind L on the bottom over here. And over here we can cancel out L. But we can't cancel out r because it is being evaluated at different positions, where here r equals r and here r is r plus dr. So those r's stay behind, and this r times dr stays behind.
Wow, that looks just like a plain old derivative now.
You're right, it is a derivative actually. If we take the limit as delta r goes to 0, that is just like taking the derivative of the stress. So here we can, because this term, the combined terms, all the forces combined equals 0, we can bring this pressure differential and length over to one side and take the derivative, essentially, of our stress. By integrating, we now find that our stress is equal to our pressure differential term over L times r over 2 plus our constant that we find from integrating over r. Now we need to solve for our constant.
Wow, that is a whole lot of explaining, but not a lot of assuming. Talk to me about your assumptions.
Oh, I almost forgot. Thanks for reminding me. Some of the assumptions we made are that this is a Newtonian fluid, which means it has a constant viscosity, that it is an incompressible fluid, which means it has a constant density, that it is steady state, which means there's no accumulation, which is why our forces combined equal 0, and that this is flowing in a one dimension, which means that it's only flowing in the z direction. Alright, now to solve our stress equation for the constant, we need to use our boundedness theory, which states that because r, if we would have an issue, if r goes to 0, we would have an issue there because you can't divide by 0, and we know that stress isn't an infinite term. So we can assume that our constant number 1 is 0. And now by using our Newtonian definition of stress, we can solve for our another differential equation but of velocity. So now if we integrate again, we find that it's this pressure gradient over negative mu, which is viscosity, times 2L over r squared over 2 plus our second constant. And to solve for the second constant, we can use our boundary condition because it's a Newtonian fluid, so there's no slip at the edges. And this proves that at the edge, at r, the velocity will be 0. So C2 is equal to the pressure differential over 4 mu L. Now we have our velocity equation. But how do we find the volumetric flow? Well, we integrate our velocity by our area, essentially. So from 0 to 2 pi and 0 to r, we take our velocity equation and integrate it by times r dr d theta. And from there, we find that our volumetric flow rate, which is the amount of beer coming out of the tap, is equal to pi times our pressure differential times big R to the 4th over 8 mu L. And now if we're trying to find our pressure differential, we can rewrite that equation as our pressure differential times our volumetric flow rate times 8 mu L over pi times R to the 4th. Now we need to take some rough measurements to find the diameter at which, to find the radius, the height at which the beer travels, and through research we found the viscosity and density of beer. Now by plugging those all into our to our pressure differential equation, and by assuming that the volumetric flow is 2 ounces per second, which is the standard for most draft beers, we can find that our pressure differential should be equivalent to 1.5 psi. As seen here, our Kegerator is at 0 psi, which is probably why there's no flow.
But wait, aren't Kegerators usually at 12 psi?
Great observation. Actually, the higher pressure is required to keep CO2 in aqueous solution with the beer. That's what produces your head and gives you that nice, foamy beer.
Wow, thanks Patrick Daly. Now I understand how beer flows through the pressure.